Welcome everyone to CS 182. Today, we're going to discuss generalization in deep neural networks and adversarial examples. Let's start with a very basic question, a question that is probably pretty important to anybody who's considering using a deep neural network model. Do deep networks generalize? Meaning, can you show them inputs that are different from the inputs that were seen during training and have them actually produce the correct answer? Okay, well, coming at the tail end of this class, this might seem like a very strange question to ask. We discussed, even at the way back at the very, very beginning, that one of the reasons why there is so much excitement and enthusiasm about deep neural networks is that they achieve very high accuracies on difficult and realistic tasks. For example, the current error rate on ImageNet classification actually exceeds human performance. Now, you might say this is because humans are not so great at classifying between very fine-grained classes, but however you slice it, it does seem like these models are doing really, really well on a lot of these benchmark tasks. But what about the mistakes? When they make mistakes, what kind of mistakes are they? This is something that matters to us a lot if we're going to think about deploying deep neural networks in realistic scenarios. If you have an autonomous car whose perception system for detecting pedestrians is a deep neural network, it'll be small comfort to you if the accuracy of that system is 99.9%, if it fails to recognize you when you're crossing the street. So what are the mistakes? That really matters. Well, sometimes the mistakes actually do make a lot of sense. Here's an example of a picture of some bees that was misclassified as a hummingbird. Why was it misclassified as a hummingbird? Well, you might imagine that because there's a hummingbird feeder in the image, it might be reasonable for the network to conclude that animals that feed from a hummingbird feeder are hummingbirds, right? That's not a correct conclusion, but it's a mistake that you could imagine a person would make. If you have no idea what a bee is, you have no idea what a hummingbird is, and you see a bunch of pictures of animals using a hummingbird feeder, you might conclude that those are hummingbirds. Here's a picture of a recent graduate of UC Berkeley. The correct label of this image is academic gown, and it was misclassified as a mosque. Now, again, this obviously is an incorrect label, but if you didn't know what UC Berkeley looked like and you just saw kind of those spires in the background, well, it's probably not a mosque, but it wouldn't be so far-fetched. Mosques do have pointy bits at the top, and you could imagine that this could be some kind of mosque, especially if you didn't know what academic gowns looked like. You might think that maybe that's some sort of like religious attire or something like that. Okay, so definitely mistakes. Clearly not mistakes that a well-informed person would make, but not like crazy, crazy mistakes, right? Well, we can actually drill a little deeper and try to understand why neural nets make the decisions that they make. In particular, we can try to ascribe credit to particular parts of the image, basically try to understand which parts of an image are responsible for the neural net making a particular classification. Or put another way, if some part of the image were altered, would that have changed the neural net's decision? So on the left, you have a picture of a husky. It's a breed of dog. And this picture has been classified as a wolf. And when we try to examine the reason, the particular part of the image that is responsible for this classification, we actually find that in making this decision, the network was not actually looking so much at the appearance of the dog itself, but at the background. The background, in this case, is snowy, and snowy backgrounds correlate with wolf in the data that was used to train the model. That actually makes a lot of sense. People photograph their dogs playing around on the grass in the park, whereas people will photograph wolves in their natural habitat, which is more likely to be snow. Not to say that all photographs of wolves are on snow and all photographs of dogs are on grass, but there is a strong correlation due to the selection bias in which photographs people tend to take. So it's not a correlation in the sense that wolves are more prevalent in snowy climates, although that may be true to a degree, but the much larger correlation here is probably due to the fact that dogs are less likely to get photographed in those environments, because kind of the classic picturesque photograph of a dog would be, playing on grass in the park, right? So it's a kind of a selection bias in your data set, or at least that would be my speculation. But perhaps what this example highlights most effectively is that when you ask your model to attain the highest accuracy on a training set, it's not really tasked with finding the real functional or causal underlying relationships. It's tasked with finding patterns. And any pattern that is helpful for it to get the right answer will be utilized. And that's not a mistake. That is actually what you're asking your neural net to do. So paying attention to the snow in the background to aid in classifying wolves versus huskies is not an error on the network's part. That is actually what you're asking it to do. It is the correct solution to maximize its accuracy on that data set. This idea is perhaps best illustrated by a story. This is a story that I borrowed from one of Ian Goodfellow's talk. It's a story about a natural learning system, not a machine learning system, but I think it illustrates some of the perils of relying on data sets and training test splits. This is a story about a horse named Clever Hans. Clever Hans was a horse that its owner thought was very clever. Its owner thought that the horse could count. And they would have these public displays where a volunteer from the audience would step forward and ask the horse, Clever Hans, what is 2 plus 1? And the horse would start tapping its hoof, and it would tap 1, 2, 3, and then the audience would start applauding because the horse had figured out that 1 plus 2 is 3. And this was not a fraud, at least not intentionally so. The owner was not somehow passing notes to the horse. There was no deception involved, at least not on the part of the owner. And seemingly the horse could count. And they studied this. They brought in scientists who would try to figure out what was going on. The one situation where the horse failed to count correctly was when the face of the questioner was obscured. So if there was something preventing the horse from seeing the face of the person asking the question, they would say, Clever Hans, what is 1 plus 2? And the horse would just start tapping and just keep tapping for as long as it was allowed to. Okay, so what was going on? Well, the horse was using the social cues. It was looking at the person because obviously a reasonable human being, when asking the horse a question, would look at its hoof, and once it had tapped out the correct number, would look up and acknowledge that it got the right answer, at which point the horse would stop. And the horse saw this during training, so to speak, and at test time. The owner was not intentionally trying to deceive anybody, and importantly, the horse was not trying to deceive anybody either, because horses don't know how to count. As far as the horse was concerned, it was rewarded for performing this task, which it could perform pretty effectively by looking at the cues from the other person. So nobody is trying to deceive anybody. Everyone is sort of attempting to do their job. This is a kind of morality tale of when the training test paradigm goes wrong. Despite the best intentions on everyone's part, despite the system actually working as intended, we still might not get what we want. We wanted a horse that can count. Instead, we've got a horse that gets really good at reading social cues. In the same way that we wanted a neural network that can classify huskies from wolves, and instead we got a neural network that's really good at looking at correlations in the background. At some level, the issue is that we simply asked the wrong question, and everybody answered that wrong question to the best of their ability. Okay, so that's kind of the high-level principle, and I'm maybe slightly belaboring this principle because I really do want to make sure that this is very clear to everybody. We're going to talk about lots of fancier, more technical things in this lecture that actually deal with the particular technical reasons for why neural networks might make mistakes. But if you kind of take away one thing from this talk, just remember the distinction between the task that you would think you want a network to solve, like being able to distinguish wolves from dogs, and the task that you're actually asking the network to solve. And remember that your network will act like the horse. It will essentially try to solve the problem by whatever means available to it without bothering very much to deduce what you actually want it to do. This is true for computers in general, but doubly so for machine learning systems. Okay, so one of the technical reasons why you might not get the result that you want in an actual machine learning system is distribution shift. We've already discussed distribution shift briefly, but I just want to make this point very concrete. One source of trouble is when the test inputs might come from a different distribution than the training inputs. And this can crop up in somewhat subtle and insidious ways. It's often especially problematic if the training data has spurious correlations, like the example with the dogs and wolves from before, but it can come up in other settings too. Here's, for example, a data set of traffic signs. You could imagine training a neural network to classify training signs using this data set. And it's a pretty good data set. There's a variety of backgrounds, lighting conditions, even some motion blur. So you might think that if you use this data set, you would get a pretty good traffic sign detector, and then you could use this detector on your autonomous car and classify real traffic signs. But of course, every data set is going to have some kind of correlation or bias. In this case, your traffic signs are center cropped and they're generally unoccluded. In reality, you might get a traffic sign that's kind of off to the side, like the stop sign, and it might be occluded by some foliage. A person would have no trouble figuring out what the sign is, but your neural network might be confused, not because it's difficult, not because it can't see the stop sign, but maybe because it never saw foliage in front of stop signs before, and the presence of foliage is out of distribution. It's very important here to distinguish between classification problems that are simply difficult from ones where you might make a mistake due to distributional shift. This is not actually a difficult problem. This example is unambiguous. No reasonable human would mistake that stop sign for anything else. Okay. Some more realistic examples of distribution shift messing up our models in reality. Medical imaging. Different hospitals have different machines. The identity of the machine strongly affects the kind of image you get, if it's an X-ray or an MRI or something like that. So that creates a spurious correlation between features in the image and the hospital in which that image was taken. Different hospitals also have different positive rates. Some hospitals get more sick patients than others. In some cases, if you have a very good hospital, you get more of the harder cases. So maybe in particular specialized areas, you might get more positive examples in one hospital than another by a very large margin. That hospital is also going to have different equipment. So now you have a correlation, a spurious correlation between the label, positive or negative, and the identity of the machine used to take that image. And that spurious correlation will, of course, be exploited by your model. So it will be more likely to classify images from the harder hospital as positive. Selection biases. All sorts of data sets that we use in reality, especially for natural images, have selection biases, meaning that the images are not just randomly occurring natural images, they were chosen by a human. For example, if these images were harvested from a photo sharing website like Flickr, maybe humans make certain decisions and they are more likely to photograph certain things in certain situations than others. And that selection bias, it might include things like center crop. So if there's something interesting in the image, it's probably in the middle. It might include a bias for canonical pose. So, for example, animals are much more likely to be photographed from the front than from the back. A lot more people take pictures of horses, speaking of horses, from the front than horses from the back, and so on. So there are many of these biases that just come down to which photographs people are more likely to take. Feedback. This is a huge source of distribution shift, which I touched on this already a little bit when we discussed imitation learning. But basically, the use of an ML system causes users to change their behavior. And this causes distribution shift. So the example that I gave back when we talked about imitation learning was a system for predicting traffic. So if you are Google Maps and you have a machine learning algorithm that predicts whether traffic jams will occur, and you give that information to human drivers, they might choose to drive somewhere else. And that might actually prevent the traffic jam from occurring. Okay, that's a good thing, but you can also go the other way. You can say, well, there will not be a traffic jam. Everyone sees that, crowds that area, and you get a traffic jam despite predicting that there won't be one. So feedback is a major cause of distribution shift. Feedback is when the decision your learning system makes affects the input that it will see. And there are, of course, many others. A very classic example, by the way, of feedback is spam classification. This is a setting in which distribution shift problems have been studied for a very long time. If you have a spam detector, it doesn't exist in a vacuum. Once spammers know how your spam detector works, they will actually create better spam that will fool your spam detector into failing to detect it. Okay. Another somewhat more subtle issue that I want to discuss in this part of the lecture is calibration. The definition of calibration is that the predicted probabilities reflect the actual frequencies of the predicted events. Okay, that might seem a little circular. Let me maybe explain a little better what I mean with an example. Let's go back to our wolf-dog example. Let's say that your neural net looks at this and it says this is 30% likely to be a husky and 70% likely to be a wolf. So these are the outputs from your softmax. What do these numbers actually represent? Well, they're probabilities. They're probabilities of some event. But which event? So when we say the predicted probabilities reflect the actual frequencies of the predicted event, what event are we referring to? Well, in order to answer that question, we need to ask, how's the data generated? If we go back to the second lecture in the course, we said that our model for how the data is generated is that a person takes the photograph, so x is sampled from some p of x, which is a distribution of photographs that humans take. And then, the way you got your training data is you took these photographs and then you had humans label them. So one way to think about the process of how the data is generated is that a person takes a photograph. The photograph does not have a label associated with it. But then another person, a labeler, maybe like a mechanical Turk worker or something like that, looks at that photograph and assigns it a label. This is literally where the labels in the training data came from. Another person looked at it and says, this is a husky. You can think of that process as sampling the label y from some true distribution p of y given x. The true p of y given x represents the probability that a person looking at that photograph on a computer screen would assign it that label. Because that is literally how the labels were assigned. And out comes husky. So when the model says 30% husky, 70% wolf, what it really means is that 7 out of 10 times a person would say this is a wolf. It does not mean that 7 out of 10 wolves look like this, or 7 out of 10 images that look like this are wolves. That is not what that means. It really comes down to the generative process that generated the data. And the process in this case was a person looking at a photograph and labeling it as a wolf or a husky. So that's the question that the neural net is answering. 7 out of 10 times a person would say this is a wolf. And in particular, that prediction is tied to the generative process for generating the images. So if you had a different distribution over images, maybe you had a distribution where someone intentionally went out and photographed wolves in warm climates and huskies on snow, then maybe this correlation would have been flipped around. But that's not what happened. So for that generative process, for that distribution over images, and that labeling process, the prediction is that 7 out of 10 times a person would say this is a wolf. Okay, that is the question the network is attempting to answer. Now, it is still a very complex question as to whether it is succeeding at answering that question. We'll come back to that a little bit later. But first, let me talk about a more obvious scenario. Let's say that you get an out-of-distribution image. Let's say you have a network that classifies between huskies and wolves. So it's just a binary classification problem, and you show it a road sign. Okay? Well, imagine presenting this to a person. You take your average person off the street, and you tell them, you've got 2 buttons, a wolf button and a husky button. Push one of those 2 buttons, and here's a picture of a road sign. Well, what are they going to do? They have only 2 choices. They can't tell you, I don't know what this is. They can't tell you it's not a husky. They have to pick one of the 2. So you might surmise that a reasonable, unbiased person would basically select between them randomly. So you would expect that a calibrated prediction in this case would probably look something like 50-50. So the 50-50 prediction basically amounts to saying, I don't know what it is. It means that one class is just as likely as another class. Now, if we had a third class, if we had like a none of the above answer, like you do on a multiple choice exam, then maybe that one would have 100% probability. Okay, so the first question we could ask is, well, does this actually happen? Like if you give an out-of-distribution example to your neural net, are you going to actually get these 50-50 predictions? Usually not. Usually you don't get this because the training data doesn't contain out-of-distribution examples. That's the definition of out-of-distribution. The network has never seen examples for which it is supposed to be not confident. It's only seen examples for which it should be confident. It's only seen huskies and wolves. Basically, none of the above, or 50-50, is not in its vocabulary. It never had to say that before, and therefore it won't. In the training data, the network only had to make confident predictions. And for that reason, for test images, even if they are out of distribution, it'll probably make confident predictions. So it will confidently assert that this is a husky or a wolf. This is not always the case, but very often this is the case. So when you give the network something that it did not expect, something that is out of distribution, very likely it'll make a confident and incorrect prediction because it only learned to make confident predictions in the training data. Now, there is another, maybe more generous question we can ask, which is, are in-distribution predictions calibrated? Is that picture of the husky, is it actually going to produce 0.3 and 0.7? Is that actually going to reflect the real frequencies of those events? Now, this is something that we think should happen because this is supported by the training data. In reality, this usually doesn't happen. This is one of the known issues of high-capacity models like neural nets. They tend to get very high accuracy, which means that the most likely category is usually the right one, but they do not tend to be calibrated. Even for in-distribution images, the probabilities that they output often do not reflect the real frequencies of those events. We don't know precisely why this is true, but one reason why we might speculate it's true is that for neural networks with such high capacity, it's actually pretty easy for them to assign excessively high probabilities to images that are actually ambiguous. Essentially, they are very, very good at predicting the label, so good that they are more confident than they should be. So that means that even for a familiar image, the class with the highest probability is probably the right one, but the probability assigned to that class might not reflect the actual frequency with which a human labeler would assign that label. It might be larger. However, there are a great many techniques that do mitigate this issue to a degree. So if you take a more advanced class on deep learning, you might learn about quite a few methods that can improve the calibration of deep neural networks. Ensembles, by the way, are one such technique, which we did already learn about. So the problem can be fixed, but a naive neural net often heavily suffers from this issue.